Thank you so much for attending the ONA webinar. My name is Maria Silveira. I'm a professor in soil and water sciences. I also would like to thank the folks attending in person here. Today I'll be talking about this project that is being funded through the Beef Enhancement Board. It's a 4-year project. We just completed this 4-year cycle, and I'm going to be reporting some of the data that we collected. I also want to acknowledge the co-author here, Yanyan Lu. She was the PhD student involved in this work, so all the data that I'm being reporting here is part of her Yanyan's PhD project. By the way, 2 weeks ago, she successfully finished, well, almost finished, but she defended her PhD and passed the exam. So soon Dr. Lu will be leaving us for another job. But and also want to acknowledge the Academians for providing the funds. Biosolids have been a very important issue in the state, and the Academians were very proactive in providing this funds when we explained that some of the research was unfortunately was not available. So anyway, let's visit. Oops, I'll go back 1 second. I understand that you probably, this is not my first talk about biosolids, at least for the folks in this room probably heard me talking about biosolids, but I just want to revisit the word biosolids. This terminology was created in the early 2000s to differentiate raw material from this material that's being processed and meets the minimum criteria to be land applied. So we're not talking about raw sludge, even though I'm gonna show you some headlines from the popular press referring to this material as something completely different. Biosolid is something that's being treated. There's pathogen levels that are within the acceptable level that the federal government requires. Also the nutrient concentration, trace metals. So it needs to have it's a very strict requirement in order for the material to be land applied. So the raw material, the raw sludge, that's landfill, that's not biosolids. In order to be land applied, you need to go through some additional treatment processes. So in terms of Florida, and I think I shared this graphic with you all if you've been to some of my previous presentation, we produce about 340,000 metric tons of biosolids per year. We used to import a lot of biosolids from other states. We no longer do that. And by the way, this slide is, I'm using Maurice Barkas, who is the DEP biosolids coordinator. I'm borrowing his slide from one of his presentations. So according to Maurice, 2/3 of the biosolids in the state that are produced in the state is beneficially reused. As you can see in this pie chart here, about 1/3 is land applied. This is mainly class B biosolids. So there's 2 classes of biosolids that are being produced in the state of Florida, class AA and class B. Most of the class B are land applied. Well, this is the most common, or used to be the most common disposal method, mainly to pastures and citrus. This 1/3 that's distributed and marketed is class AA, that sometimes is marketed as fertilizer, sometimes is used as a filler for inorganic fertilizer, and about 1/3 is landfill. The current biosolids regulation is under revision, so this pie chart might look slightly different depending on how the final regulation will look like. Maybe some of the land application will decrease significantly because of the new requirements. And this is a very interesting piece of information. I wasn't aware. 30% of the Florida population is on-site sewage treatment, so septic systems, which I didn't realize the number was so high. So I want to put things into perspective. Biosolids has been closely related to nutrient issues, water quality problems. But let's look at the overall Florida. And here, for this particular presentation, I'm focusing on phosphorus. So what are the sources of phosphorus in the state of Florida? And by the way, I have to acknowledge the Academians again, because we're working on developing more accurate estimates for this pie chart. We're collecting data. These are all estimated numbers based on data sets that are available through different entities. So there's a lot of uncertainty associated with these values. But if you look at the data that I'm presenting with some of what my colleagues presented in the early 2000s, it's pretty similar. So we import in Florida, we import about 58,000 metric tons of phosphorus per year. This is annual, and this is based on estimate from 2014. Most of this phosphorus come from farm fertilizer, about 42%, even though phosphorus fertilizer in agriculture has been drastically reduced in the past decade or so, more than 30% reduction in phosphorus fertilizer use. It's still, this farm component still represents a significant component of the phosphorus budget. Livestock manure, and if you look at the biosolids, it's a relatively small contribution compared to the overall Florida P imports. And one thing I really don't like about this pie chart and the way that, and I'm following the same format that's being reported previously by other authors, it completely ignored the human component. So we know we have, I don't know what is current, the population, 21 million, 24 million people. When we exclude the human component, I don't think we have a very accurate picture of the Florida P budget. So using another data set, this is EPA data set, and when you include the human components, and again, there's a lot of uncertainty associated, so the number might be slightly different based on the data that we're currently collecting. So now the total P import jumped from 50,000 metric tons to about 93. So it's a 60% increase, and the 60% increase is due to this human component. So all the human waste that's produced, and this, by the way, is I'm excluding biosolids. So all the solid waste, food demand, no food demand, it increases the total amount of phosphorus that's imported in the state. So no food demand, for instance, soap, pet food. There's some research showing in the Great Lakes, in St. Paul, Minnesota, showing that about 40% of the phosphorus input in that watershed is due to pet food. So if you think it's big metropolitan areas like Tampa, Orlando, Miami, imagine the amount of phosphorus that's associated with this human demand. So we're trying to come up with more reliable estimates. And if you look at in this particular pie chart, biosolids represent a very small fraction of the overall P budget, only 5%. But there's a lot of attention being focused on that part of the pie chart. And that's where the data, but I just want to provide this, start with this just to provide you some perspective. Also, when we look at the fertilizer use, it's very difficult, by the way, to distinguish between farm and urban. The urban fertilizer use is based on the population, so there's a lot of assumptions involved in that 2% based on the population on an average. And I imagine that an average citizen in Okeechobee County probably use a very different amount of phosphorus fertilizer urban than somebody in Miami-Dade. So I imagine that those averages are also, the range is extremely large. But if you look at the P fertilizer, and it's easier to track farm fertilizer versus urban, like I said, the urban is based on estimates. But even if you look at the farm and the state, the fertilizer use is not well distributed across the entire state. About 25% of the P input goes to that county, West Palm Beach, and the surrounding area. So it's about 1.3 million acres, and it's listed as a majority as being non-ag use. So that's the type of discrepancy we're trying to get more reliable estimates. Oh, let's switch back to biosolids. Even though that's a relatively small contribution to the overall phosphorus budget, it is still a nutrient source that can, if not managed properly, can eventually cause environmental problems. So these are highlights, and I copy from various public press, newspapers, websites that were published. It started all this very negative popular press, probably started mid of 2018. And you see the very negative connotation associated with biosolids. So you see, I start my presentation by introducing to the term biosolids, and I indicated there's a lot of regulations involved in land application of biosolids. But here, these public press articles refer to human waste. It's very creative, the way that people define biosolids. But I think it just feeds into that negative connotation, and people that are not necessarily familiar think that this material will always cause environmental problems. There's very little evidence or no evidence suggesting that there's a relationship between biosolids use and water quality. But evidence can only be confirmed by science, and this is what I'll be sharing with you. And this is, by the way, this is just a small component of the biosolids project. So there's other studies that I won't be referring to today, but anyway, let me move on to the next one. So given all these controversial issues associated with the biosolids, mainly because of yuck factor, it's people don't seem to bother to apply animal manure because it comes from cows or sheep or whatever, pigs, chickens. But when you talk about human waste, the human component really scares people. But if you think our very rich Florida soils, right? Our Florida soils are extremely rich, right? No, they are sandy, low organic matter, low water and nutrient holding capacity. So when we have an amendment, and I'm not calling biosolids a waste material because to me it's not a waste. It contains so many, it can provide so many benefits if used properly. So they are excellent candidates for pastures to replace inorganic fertilizer when pastures are fertilized, which that's not usually the case, but they can replace inorganic fertilizer. And the reason why forage is a good candidate, pasture, perennial pastures in general are good candidates is they have a very extensive root system. They have a very extensive growing season. So that minimizes any potential of nutrient transport. And I'm going to show you some data to prove that what I'm talking about. And also because it contains organic matter and a lot of nutrients, it can also improve some of the soil physical, chemical, and biological properties. Most of the nutrients, mainly nitrogen, but also phosphorus, they are not immediately available to the plants and they're not very soluble. So biosolids act as a low release source of fertilizer, which can also be beneficial in some cases. It's just from the agronomic standpoint, we need to plan ahead. So we know, and I'm going to show data also demonstrating this low release from an environmental perspective is good because it allows the plants to better utilize the nutrients in the biosolids. But at the same time, if you don't apply the biosolids at the right time of the year, the plants can suffer. You won't produce the same amount of forage. The challenge is, of course, it's much easier to apply commercial fertilizer. You can pick the formulation you wanna. Biosolids are more challenging to be spread. So in terms of physical characteristics, you can have anything like this. I'm not sure folks can see. This is a pelletized material that you can buy at Home Depot. So relatively easy to spread. Or you can have anything that ranges from this, which very low moisture content, very easy to apply, to a liquid material or a cake material that has 15% solid. So extremely difficult to apply. And of course, the composition may not necessarily be what you need for your particular crop. So there's some challenges. And another challenge is the nitrogen to phosphorus composition. Plants, crops in general, they usually need about 6 parts of nitrogen, 6 to 8 parts of nitrogen to 1 part of phosphorus. Usually this material contains much more P enriched. So if you are to supply the plants with the nitrogen requirements, you most likely gonna end up over applying phosphorus because the plants, this imbalance between the plant requirement and what most biosolids contain. Is this a problem? It can be. Depending on how often you apply biosolids and the application rates. We kind of pushed a little bit in the study. We applied biosolids for 4 years and at nitrogen-based rates. So we knew that we were over applying phosphorus, but that was our goal. We want to see if over applying phosphorus, what would be the impact on water quality. So in order to address some of those concerns, and even though there's been research done in Florida addressing biosolids issue, most of the research has been done in very controlled environments, so greenhouse, lab benchtop, which are great to answer some questions. Even the rainfall simulator that we use sometimes, they are great tools to answer some questions, but depending on the question you're trying to answer, you cannot ignore the hydrologic component, the soil component. So we need to have some long-term, well-instrumented field studies to address some of this question. Of course, the word long-term and instrumented translating to high cost. And that's why I acknowledge the Cattleman, because we were very fortunate to acquired the money from the cattlemen to establish this long-term instrumented field site that we can address not only questions related to nutrients, but other questions like pathogens, soil carbon sequestration. So we established this study the site was established in 2016, and we've been collecting data since 2016. And the goal was to look at both the agronomic impact or forage responses, but as well as potential impact of repeated biosolids application on water quality, greenhouse gas emissions. I mentioned that the imbalanced nitrogen to phosphorus ratio. So how can we come up with a better way to manage these materials that we know that will be over applying phosphorus? So another waste material is called biochar, which I don't have a sample here, but it's a carbon-rich material that can absorb nutrients. So I said one of the hypotheses we tested, how about if we co-apply this material that can absorb excess nutrients with the biosolids? Maybe this will be a strategy to reduce any potential environmental problem. And we did that. So establishing, again, I want to acknowledge Yanyan. Doing field work with biosolids is not the easiest thing, not the most pleasant thing. So you can see in this picture here, the cake material that you used. By the way, H&H liquid disposal helped us. They brought us the material, you see their truck. Sometimes we were not very happy with the material that they were giving us for free, and we kindly asked the driver if he could bring us another load, and they were very patient with us. That's a better word to use. And they brought the material that we wanted. But anyway, and we had to weigh these materials in individual buckets and then manually or with a manure spreader spread to the sites. So again, it takes a special type of person to dedicate 4 years of their life working with this. And this is not, we also have the pelletized. Let me tell you, this cake, it was not a very pleasant stuff to work with. And the biochar proved to be also, we want to use things that mimic what could be available for producers. So we bought biochar from this facility in Florida, and it was an extremely powdered, fine material that proved to be extremely difficult to apply. So I have a picture of Yanyan and myself here after the biochar application. We look like coal miners. But anyway, that's for the sake of science. So in terms of instrumentation, this is what we had in the field. I'm going to show you this schematic representation. We have lysimeters. This is a drain gauge lysimeter, just to give an idea in terms of the cost. When people say, oh, research, why cost so much to do research? This piece of instrument alone is about $1,500, and we have 20 of those in the field. This device allows us to collect all the drainage water that is coming from that particular treatment. So we know the volume of water that's draining, but we can also analyze the water. So that's how we did the water quality assessment. We also have soil moisture probes with data logger. We're looking at the negative aspect, but we also want to see, well, will biosolids increase the soil water holding capacity? So that's why we had the soil moisture. We had pressure transducer, basically this piece of equipment that also costs about $1,200, $1,300, measures the fluctuation in the water table. So in the summer, the water table approaches the surface. It's important because that's where most of the nitrogen and phosphorus flow would occur. So we want to be able to, in order to interpret the water quality data, you need to know where the water table is. And this is constantly monitoring our sites. And I have also to thank the staff here for helping me install this instrument. It was probably the worst job I've ever done in my life. I ended up in the chiropractor. So thanks Tom and Ryan and others that helped us install the lysimeters in the field. So this is how the field looks like. If you've been to one of our recent on a field days, you're gonna say Maria only talks about biosolids. I'm very proud of this study. So you've probably been to this site, but this is how the plots look like. This is the lysimeter. You don't see much, but everything is below ground. Here, the soil moisture sensor, the data loggers, the sensors you cannot see. We also have chambers, static chambers that we measure the gas emissions. But let's look at the data. So I'm focusing now on forage responses, and this first graphic refers to the 2017 growing season. The next one is 2018. I'm not going to show everything. I'm trying to summarize. Basically, remember what I said, and this is, I apologize, this is in kilograms per hectare. I know most people prefer pounds per acre. Pounds, we can, just for the sake of presentation, let's assume that it's the same. It's about 11% less. But what I'm more interested in is not as the actual number, but the trend. So this is, and by the way, this is first paper from Yanyan's work that's already been published. So also very proud of her work that's published. That's how we validate our research. If I do this, show the data, but I don't publish, my peers don't criticize my work, my science has limited meaning. So this is something that's being validated by my peers. It's published in one of the top journals in my society. So I applied the biosolids in 2017, probably around April, if I remember correctly, it's April 26. 60 days later, we harvest the plots, and we repeat the harvest every 60 months. Every 60 days. So 3 harvests per year. I mentioned that biosolids are a slow release source of nutrients. So let's pick one here, just an example. For instance, this material here, you see this is actually this material, the thermally dry class AA biosolids, a pelletized material. You see the production was not that great in June because the material, that nitrogen was still tied up. As the nitrogen became more available, it was mineralized, you see the increasing forage production. Conversely, if you look at the inorganic fertilizers were designed to be fast released. So you give to the plant and the nutrient will be immediately available. And that's, you look at this dark shaded bars here, this is inorganic fertilizer. By the way, it's nitrogen and phosphorus fertilizer. You see that the forage production decreases over time. So most of the nutrients are consumed early in the season. Towards the end of the season, that's when we need more the fertilizer effect is gone. So there's another advantage of biosolids. You can have that more continuous forage production throughout the growing season and have production during the times of the year when you need the most. And by the way, just want to say one more thing. You look at ignore the lowercase letters. Let's look at just the higher uppercase letters. You see there's no difference between the biosolids and inorganic fertilizer. We're going to revisit that. So let's move on to the 2018. 2018 the response was slightly different because unfortunately we're not able to apply biosolids early in the spring. We end up applying materials in June. So you see that most of the forage production occur in the first harvest, and December, as everybody in this room knows, Bahiagrass is dormant, so it doesn't produce much. So there's some slightly difference between 2017 and 2018, but more importantly, when you look at the cumulative Bahiagrass production for the year, here you have controls, by control meaning no nitrogen or phosphorus addition, and then you have the different materials, including inorganic fertilizer. There's no difference between all the sources in 2017, however, in 2018, there's only one biosolid source. So if you see the letter A here and the letter A in the inorganic fertilizer, means that they are the same. This average is the same. So the reason why some of the other biosolids produce slightly less Bahiagrass, the Bahiagrass production was slightly lower, was because this material was highly more soluble. So I applied the biosolids late in the season. You need a more soluble source because towards the end of the growing season, Bahiagrass is dormant. So it doesn't matter if nutrients are available, Bahiagrass is not gonna. So the bottom line, the take-home message is, if it's a normal, spring application, it really doesn't matter what source of fertilizer you're using. Now, if you're using towards the middle or the end of the growing season, it's important to have more soluble nutrient sources. I'm not going to spend too much time. What I'm showing here is crude protein, CP here meaning crude protein in percentage, and in vitro digestible organic matter, a measurement of digestibility. Basically, the take-home message without even looking at this data is, doesn't matter what source of nutrient you're applying, biosolids or inorganic fertilizer, crude protein and digestibility will be the same. So this is part of the forage, the agronomic assessment. Really no big differences whether you supply Bahiagrass with fertilizer or any of these different 3 biosolids material. And one interesting thing, we know how much nitrogen and phosphorus we're adding, so we want to see how much were the plants able to capture in the above ground tissue. So it's interesting, if you look at the nitrogen, for instance, and this is the amount of nitrogen that we added in 2017 and 2018, and again, we have data for the other years, but just want to pick those 2 years. So for instance, for the this AA biosolids. I apply 160 pounds of nitrogen per hectare, which let's call pounds per acre. And the plants were able to utilize 100% of the nutrient that I apply. So water quality, when we think in terms of potential environmental impact, nutrients will only be lost if there's any nutrient in the soil. So plants were pretty, again, this data confirms that first assumption that I made, that forages are excellent candidates for biosolids application because they can utilize all these nutrients that we apply. So this is for nitrogen. And if you look at the phosphorus, about between 18 to 46% of the phosphorus that was applied was actually recovered by the plants. So plants don't use phosphorus quite as efficiently as they do with nitrogen. So for instance, in this case here, the same biosolids, we apply 70 kilos of P, which is way above the agronomic recommendation, and plants use about half of that, 30 kilos of P. So what happens to the remaining 50%? That's the next piece in our puzzle. Is it lost in the water? Does it accumulate in the soil? Because especially phosphorus, there's no way phosphorus doesn't disappear. If you don't recover in the water, or if it's not the plant uptaking it, you have to measure it. It doesn't disappear. Nitrogen is a little bit more difficult to track because there's some nitrogen gas that can be emitted, and we may not be able to capture those emissions. But let's move on to phosphorus only 50% was accumulated in the plant. What happened to the other 50? Did it leach with the water? And this is the water. Before I show the water quality data, I need to explain what this means. And I understand this is a very busy graphic, so let me walk you through. So the open circles here is the drainage volume. Remember I mentioned that I had that device? So this is the amount of water that's moving, that I'm collecting in the device. And each of these points here represents one sampling event. So if I'm not mistaken, Yanyan went to the field at least 36 times during the course of this 3-year study. So you see the dates here range from 2016 to 2018. So every time they're more than, can't remember what was the criteria, 0.4 millimeters, or no, for 0.4 inches, she'll go to the field and collect water. Or every time that we had a major rain event, she'll go. So this is, I'm compiling all the sampling events that she conducted during this 3-year. And here the red arrows represented the data that we applied these amendments, so biosolids or inorganic fertilizer. And one thing that I forgot to mention here, the squares are the water table. This is a typical for Florida for folks that are not familiar. In the summer months, for instance, here, this is June 2016. You see the water table is about 15 centimeters. So the water table fluctuates during the winter and the summer months. Usually in the summer months, the water is close to the surface, or sometimes, as you see here, 0 centimeters. That means that there's water standing in the plots. The reason I have this 30 centimeter or 12 inches marked here, that was the depth of the lysimeter. So quite often, especially in the summer months, the water table was, was above the depth of the lysimeter. So why that's important? Because that hydrology and the fluctuation in the water table is gonna dictate how nutrients move from this site. And this is, I'm talking about experimental site, but that also happens if it was a pasture, a commercial pasture operation. The mechanism and the processes are the same. Only thing we have a smaller scale that we can monitor for those things. So when you look at, and I'm gonna move relatively quick here, this is soluble reactive P in the water. There are different forms of phosphorus in the water. This is the most bioavailable form of phosphorus. Usually soluble reactive P is pretty close to total P, but I'm showing you is soluble reactive P concentration as a function of the sampling date. And if you remember, I'm gonna ask you to keep in mind the previous figure that I showed you with the water table fluctuation. So Yanyan did 36 water sample collections, and in only 8 sampling events, she detected difference. So this red asterisk represents time of the year where she detected difference between her treatments. And if you look at the square here, the square is representing the inorganic fertilizer. So when we saw these peaks in leachate P concentration, usually it was associated with inorganic fertilizer. So you see the biosolids, and it's very difficult to distinguish between the biosolids and the control plots. Which it's kind of disencouraging to tell a student, well, you go to the field 40 times during these 3 years, and you're only gonna see difference in 4 or 5, maybe, in this case 8. So not very encouraging. I'm wasting my time going to the field doing this and I don't see any difference. But I think that's the importance of this data set. I'm gonna show another, not sure, maybe I don't have here, but the cumulative phosphorus, mass of phosphorus that was leached from these plots, there was no difference between biosolids and control. When we saw those peaks, they're usually associated with inorganic fertilizer. The reason for that is, again, it goes back to the solubility. Phosphorus in inorganic fertilizer is highly soluble. So we expect that type of response. I'm gonna move a little bit quicker here. This is the same data for nitrogen. So we were applying about 240 pounds of nitrogen per year. That's a lot. That's a lot of nitrogen. If you think producers, when they are using inorganic fertilizer in a graze pasture, if they can afford, they'll probably apply 50 to 60 pounds of nitrogen to the acre, per year. So I'm using much greater rates here, it's 240. So at least 4 times more than what it normally will be added with inorganic fertilizer. And if you look at, for instance, nitrate, let's look at nitrate. I know my y-axis here is messed up. So this is leachate nitrate concentrations in milligrams per liter or parts per million. So again, out of the 36 sampling events, only 7 there was a treatment effect. And again, if you look at the treatments that result in greater nitrate leaching, it was again the inorganic fertilizer. But it only happens during the time of the year when the water table is close to the surface. So if you look at, for instance, this particular, and this slide is from Yanyan, she picked this particular sampling event that produced the inorganic fertilizer resulting in greater ammonium nitrate and total nitrogen leaching. And she looked at the particular, and what happened that particular day? Was there an environmental condition? Was there heavy rainfall? And you look at the water table, that's when the water table was probably near the surface. So that's the time of the year where we have the greatest likelihood of nutrient transport. What I want to show you, it's a lot of data here. What I want to show you, this is the amount of nitrogen that was added, and I want to show you the percentage. This is the kilograms per hectare that was leached. But what I want you to focus is the percentage of mass of nitrogen that was added that leached. So for instance, biosolids, 2% of the nitrogen that was added end up in the leachate. So fairly small amount of nitrogen, only 9 to 10 kilos. You see also there's no, I mentioned biochar as being maybe a promising management strategy. Unfortunately, based on the materials that we tested, there's no agronomic or environmental benefit associated with biochar. Even though folks claim a lot of positive things, at least the materials that we tested, there's no increase in production, no reduction in phosphorus or nitrogen leaching. And so again, back to the percentage of the nitrogen that was leached, if you look at commercial inorganic fertilizer, the percentage was slightly greater. And in fact, biochar, it kind of reduced the amount of nitrogen that was leached from inorganic fertilizer. When you eliminate the control and just compare biosolids with inorganic fertilizer, about 2% of the nitrogen that was added leached from the biosolids versus 11. So there's a significant difference. And if you look at the same thing for phosphorus, again, phosphorus is in this part of the state is more critical issue. We apply, this is the P loads, and this is P, not P2O5. So keep that in mind. It's a lot. We're saturating the soil with phosphorus. We're over applying P, way above the agronomic recommendation. And look at the mass of percentage of the phosphorus that was leached. Really doesn't matter if you're applying. So this means this P value means it's not statistically significant. So that means that 0.1 is not different than 0.2. Only 0.1% of the P that was applied, the 414, was actually leached. Why is that? So I said, well, plan to use 50%. It's only leaching some negligible amount. Where is the phosphorus end up in? Definitely not in the water. I'm gonna skip that. That's repeating what I just said. I'm gonna skip this conclusions as well because I think I mentioned there is no based on these 3 years of data, there is no impact of biosolids application on nitrogen and phosphorus leaching, no benefit of biochar. And what's the main driver in the system is the fluctuation in the water table. So every time we have water table approaching the surface or have rainfall, that's where most of the leaching occurs, and mainly associated with inorganic fertilizer. So the soils that we were using for this study exhibit relatively high sorbing capacity, desorbing capacity. So that means that they retain a lot of that phosphorus that was not. So we apply the phosphorus, plan to use a portion, a very small fraction was leached. Most of the phosphorus accumulated in the soil. I'm not going to show the data today, but Yanyan is going to be publishing that data in the near future. We also analyzed greenhouse gas data, greenhouse gas emissions, because there was another concern when you apply a organic starch, you have the potential to increase, especially methane. That's the rationale behind. The data is kind of boring because there's nothing, there's no difference. Even though, again, there's another thing that we measure, spend a lot of time in the field and in the lab, and basically it's a flat line, but we need that type of data. So this is, I'm gonna go over quickly how she did. It's a very elaborate process. I'm just rushing here to finish the presentation in a reasonable time because I'm hungry too. But it's a lot of effort, and this is the data. Well, I'm gonna move to nitrous oxide emission because I think that's more important. So you see again, the blue arrows represent the time when we apply the materials, and you see these peaks in nitrous oxide emission. Nitrous oxide is a very potent greenhouse gas, more potent than carbon dioxide and methane. Most of the nitrous oxide emissions happen right after the amendment application, except in 2017. So you see that increase in nitrous oxide emissions for all treatments, but it's also related to environmental conditions. So I'm not going to show the same graphic again, but usually when you have those peaks in greenhouse emissions is when we have the water table close to the soil saturated with water. Methane, again, very boring data set. You see everything is baseline. There's nothing to be shown here. There was one event here when the water table was close to the surface that biosolids resulted in greater methane emissions. But overall, for the year annual or the 3-year study, we didn't see any difference between the treatments. So that means adding or not adding nutrients via biochar or inorganic fertilizer didn't result in any significant difference in greenhouse emission. Our greenhouse gas emissions are fairly small, so it's even difficult to measure, differentiate baseline from the treatments. So what Yanyan is working right now is this mass balance. During my PhD, I was taught this concept. You add something in the system if you cannot track where you end up. So for instance, let's use phosphorus. That means your study has pretty big flaw. So if you are not measuring all the components, you're assuming or calculating by difference. Well, if the plants didn't use it, that means that it went through with the water. That's a wrong assumption because there's so many components and these are all interrelated. So Yanyan is currently working on this mass balance approach. So she knows how much she knows how much she added. So this is for the entire study. And this is 100% of the phosphorus that was added into the system. She knows how much the plants utilize. She knows the changes in the soil. And hopefully this error, 15% is a pretty decent error. So she can account for, make very definite conclusions where the phosphorus migrated. Definitely not the water. I was really surprised that with this 0.1%, but when you compare our data with the literature, that's pretty consistent with other previously published work. And by the way, we're measuring the soil up to 90 centimeters, as deep as we could go. Of course, there's way to measure below 90 centimeters. We don't have the equipment, but so most of the story here about phosphorus, most of the phosphorus moved vertically in the soil profile. Plants were using all the phosphorus that was present in the first top 12 inches. So there was a little bit of vertical movement in the soil profile. So it decreased, soil P decreased in the upper layers, but increased in the deeper layers. And she's trying to do the same thing, excuse me, for nitrogen. Like I said, error here is slightly greater, and even 23% is pretty decent So most studies you're gonna see, you add nitrogen, you measure how much it was plant uptake, and usually you cannot come up with and usually that's accounts for about 50% of the nitrogen added. In our case, it's 64. And usually people don't measure the other 40, 50%. So that's what I think that's another value with this data set. She's measuring all these different potential outputs of nitrogen. With that, I think that's my last slide, and basically repeating the same thing. Our 3 years of data show there's a lot of there's some agronomic benefits associated with biochar. It can replace inorganic nitrogen, reduce the same amount of forage, same nutritive value. No impact of biosolids application, repeated biosolids application on water quality or greenhouse gas emissions. And another conclusion was that the climatic conditions, in this case, rainfall and water table, had a much greater impact on both greenhouse gas emissions and water quality than the fertilizer management. And I'm just repeating again the biochar, and I need to be careful how I state this. The biochar materials that we evaluated for this study show no agronomic benefit. So I'm not saying that all biochars don't work. What I'm saying is the one that we tested showed no benefit, even though there's some claims that would provide all these environmental benefits. Again, when we conducted a field-based study, we didn't see any of those benefits. Again, I want to acknowledge the Cattleman Enhanceable Board for providing the funding, and they continue to provide the funding. So we're going to expand. We're in the process of reevaluating the treatment since we closed this 4-year cycle. There's no residual effect, so that means that we can maybe address other questions. So we have a new PhD student that will be involved carrying on Yanyan's work. His name is Leandro Vieira, and we'll be looking at some other research questions. I also want to thank Cindy Hawley, she was a biological scientist that helped me during this 3-year study. Without her, I don't think we'll be able to complete this project. Of course, the staff here, the other students, interns that helped throughout the process. And H&H Liquid Disposal for bringing us the material for free. I felt really bad when the driver had to turn the driver around and say, hey, can you please? Cindy will make the puppy face and say, can you please bring us another load? And the guy would normally bring with no problem. So anyway, if we don't have a chance to, if you, for some reason, you don't have time to ask questions, here's my contact information. Before I finish, I don't have the paper in front of me, but the next webinar, I don't have the title of the webinar because I wrote, it's April 14. Chris Privet will be providing an update about beef cattle economics. I don't know exactly the title of his, Andrea is gonna kill me. But April 15, the second Tuesday of the month is when we typically host a webinar. So please, hope you can join us next month for our webinar. I'll be happy to take any questions. Thank you. Thank you. Folks attending online, if you don't have any questions or I don't see any questions popping up, feel free to reach me by email or phone if you want to follow up. Thank you so much.